In today's video, we're going to talk about this little flashlight kit called the Humanalight. It's really just a flashlight that's designed to give you usable light out of basically depleted AA batteries. And also the sale of the kit supports a very interesting cause. So in order to light like a 3 or 3.5 volt LED from a depleted battery, a simple two-transistor relaxation oscillator is used. So we'll spend some time reviewing the schematic, making some measurements on it to see how it works, and we'll also discuss the cause that the sale of this flashlight helps to support. Here's the schematic for the relaxation oscillator that makes up this flashlight. Just a simple relaxation oscillator with two transistors, and we'll go take a look at some waveforms on the scope in a moment. Basically the way this works is initially this transistor turns on, being turned on through that resistor. That basically starts building current up through this inductor. And then at some point, a little time later, this transistor turns on. When it turns on, it pulls the base of this transistor down, shutting it off. And now that magnetic field that's charged up in this inductor starts to collapse, reversing the voltage on that inductor, basically boosting it up above the supply from the 1-volt battery, and dumping that current down through the LED, lighting the LED. That continues for a while until the field collapses enough on that inductor for this transistor to then shut off, and then the process repeats. This one turns on, we charge up the inductor again, and the cycle continues. This will all become clear when we look at it on the scope. We're going to be probing 4 voltages. We've got 4 channels, so let's use them all. Channel 1 will be looking at the collector of this transistor, which is also the voltage across the LED, so it'll be apparent when the LED is on. We'll also take a look at the base voltage of this transistor here to see what's going on there, and also look at this voltage here, collector of this transistor, base of that one, to see what's going on there, as well as the supply voltage. And that'll be the yellow channel, cyan channel 2, magenta for channel 3, and green for channel 4. We've got the circuit hooked up here to a power supply because I wanted to run it off of a supply that's even lower than the dead AA batteries that I have. So we're actually running the circuit off of just 1 volt. And I've got the 4 probes hooked up as we described earlier. Now it's helpful to look at the circuit from initial startup. So let's do a single shot capture on the scope to grab the activity in the circuit when we first power it up. And so we'll turn the circuit off, set the scope to do single shot capture, and turn the circuit on. Alright, let's take a look at what we have. Channel 4, the green trace, is the power supply. And you can kind of ignore the bouncing that's going on here. That's just some switch bounce when we flip the switch on. So we can see the power supply is going from ground to 1 volt. And immediately after we do that, we can see this guy here, which is channel 3, is coming up to about 0.6 of a volt or so. Now channel 3 is the base of this transistor. So that means the 10K resistor is turning on the base of this transistor right away. So with that transistor turned on, that's going to start pulling current through the inductor. Now of course with an inductor we can't change the current instantaneously, so what happens is the voltage at the collector here goes right down, and basically the transistor goes into saturation, but at very low current levels. So the inductor really is just going to appear across the power supply from 1 volt down to near ground here. So if we take a look at that, that's channel 1, we can see that's sitting just barely above ground. So whenever we put a fixed voltage very quickly across an inductor, the current just ramps up linearly. So what's happening during this period is that the current is ramping up in this inductor and building up a magnetic field around that inductor, storing energy. Of course, also what happened here when we first powered up, there was no charge across this capacitor. So this voltage is sitting down near ground, so is this. So that's why this transistor is off. If we look at the cyan trace, we can see that's sitting down near ground. But we can also see it's starting to charge up. What's happening is that this 100K resistor is charging up this capacitor. So even though this side of the capacitor is being held down near ground at this collector, this side's starting to come up. So what happens is once we get to the point where this transistor starts turning on, this is where all the action happens. Okay, so as we start to turn this transistor on, that means this collector is going to start pulling some current through this 10K resistor and start dropping this collector voltage. When this collector voltage drops, the base voltage of this transistor drops. That turns off this transistor. So now this transistor is no longer pulling current through this inductor. Now, as you know, the current through an inductor can't change instantaneously. So what happens is, as the current gets shut off here, this current is going to continue to flow because of the collapsing magnetic field around this inductor. And since that current is continuing to flow, it can't go in here, so this voltage starts raising up. And what happens is the voltage continues to raise up and actually kind of pivots, if you will, around the positive supply and brings the voltage up above the positive supply and keeps doing that until the LED turns on. Okay, and as it's doing that, it's charging up this capacitor, so it's building up a positive charge like this across that capacitor. It's raising this voltage up, and it gets to the point where this LED turns on, and now the collapsing field and the falling current that's being sourced out of here is lighting up the LED. Now we can see that's what happens here. The base of that transistor is being shut off. Okay, that's the magenta trace right here. Okay, as soon as that happens, the voltage at this collector swings well above the supply all the way up to the point where the LED gets turned on, and that's what happens right here. Okay, and now the current is starting to decrease through that being sourced by that inductor, so we see the voltage starting to decrease here as well. We've charged up this capacitor when that happens, so now I've got a pretty good voltage across here, but now as this voltage begins to fall, we're also going to start collapsing the voltage at the base here as well. It's very tough to see that here, but there's a slight negative tilt on that as well. So what that's going to cause is this transistor to very slowly start to turn off. As it turns off, its collector voltage begins to rise, and we see that collector voltage beginning to rise. So as that collector voltage rises up, so too does the base voltage of this transistor. So as it's rising up, this transistor again starts turning on. Once it starts turning on, it again starts pulling current through that inductor. Okay, so as soon as it starts pulling current through that inductor, that voltage that was sitting up here turning the LED on gets yanked down almost immediately. And we can see that happening right here. Boom. Now because that voltage is dropped so fast, and there's a charge across this capacitor, that the other side of that capacitor follows it down. So that's this transition here. This is actually the base of this transistor here. He got yanked down because that voltage is just boom. The capacitor voltage is kind of being pushed down with it. So we're yanking down and turning this transistor off hard. So it's kind of like a little bit of a positive feedback thing. As this thing starts to shut off, the action of this output turns it off really hard. So now what happens during this period of time, we're charging up that inductor again. The voltage is low, so the LED is off. But now this voltage begins to charge back up through the 100K resistor. We see that going on here. At the same time, the current is ramping up through the inductor. Okay, and we reach a point where the current ramps up to where we're going to start hitting the current limit, if you will, of this transistor. We've got a fixed amount of base current coming through the 10K resistor. That current times the current gain of the transistor sets essentially what the collector current, maximum collector current would be under those conditions. Once that happens, then we start to see a little bit of a rise on that collector voltage. As that rises up, the base voltage here on this transistor follows it. Okay, and then the whole cycle starts all over again. This transistor turns on, boom, and that turns this transistor off. The voltage rises up, through the inductor. As it basically collapses, the field collapses, it sends its current through the LED, and the whole process starts over again. If we put the scope into continuous run mode, we can see that's basically the cycle that keeps going here as the voltages or the circuit continues to operate. I'm just adjusting the voltage slightly here. You can see if I raise the voltage ever so slightly, I'm about 1.1 volts here. You can see the frequency of oscillation changes a little bit, but the basic operation of the circuit doesn't change. So that's how this little relaxation oscillator works. So I mentioned when we started that the sale of this little flashlight kit supports an interesting cause, and the cause is Ears to Our World, and this is the website here, earstourworld.org, and they provide some interesting technology to rural, remote, and impoverished regions of the world, mainly in the form of self-powered radios. With the belief that having access to information from around the world will aid in the education of these regions. So interesting cause, and certainly a very interesting little circuit, and one example of how to power up a 3-volt LED from as little as a 1-volt power supply or depleted AA battery. Anyway, thanks again for watching, and comments are always welcome.